Really pleased to welcome Carrie Anderson. Carrie is recently retired from the CFS. Who's spent most of his career doing what? Fire weather stuff, right? Fire weather investigations and.
Yeah, I guess so. I'm a little thumbnail in the corner there. Do I take up the full screen eventually? Yeah, mute.
Yeah, Carrie, you got to
off.
share your screen here. We're not we're seeing your face. We're not seeing your.
Oh yeah, no, I thought I'd introduce myself. So yeah, I'm Carrie Anderson. I used to work for NRCan. I retired about 2017. So what's that? 7 years ago? Jeez. But since then, I've been working with Environment Canada, Environment and Climate Change Canada. I figured that if they're going to pay me 60% of my salary, I'm better off doing that than finding something else to supplement it. And sure enough, Environment Canada picked me up. So I've been working with Environment Canada primarily with calculating smoke. I've got my model called the Canadian Forest Fire Emissions Prediction System, and that gets fed into the Environment Canada's firework. A lot of the concepts in CFEPS is also used in UBC's Blue Sky, but I will not belabor that too much here. So I'm going to open the share tray here, and hopefully I'm going to. Okay, let's try this first here. Let's see how far we get. Wow, do you see that?
Yeah, we see your PowerPoint.
Okay, there you go. Okay, so I asked the group to do a simple exercise, more of a conceptual exercise than a clear-cut black and white answer set. I mean, the intent was to get you thinking about smoke as opposed to flames and combustion. So the introduction was simply an exercise asking how the following fire behavior and weather parameters would affect smoke concentrations basically near the surface. Okay, and when I got the answers, it was really quite fascinating. About half the people, well, there was kind of a mixed review of how the rate of spread affected smoke concentrations, but half agreed that fuel consumption led to an increase in smoke concentration. Fire intensity, again, a lot of kind of mixed responses. And finally, there was a clear consensus that vertical instability decreases the smoke level. So just as a simple exercise, just so that you guys can follow, I kind of did a little drawing. I'm a visual person. So I kind of drew a forest fire, 4 time steps, T1, 2, 3, and 4. And if anybody has any questions, you just pipe in and we'll discuss them. So orange.
Carrie, sorry, have you started your presentation yet? We're still seeing your title slide.
Oh, okay.
Because you're talking about a diagram. We haven't been following. We're still looking at your title.
Okay, let's start again then. I was kind of worried about whether that would work or not. I often have trouble in MS Teams. So I'm going to try close. Okay, we'll try it again from scratch. Desktop. I'm going to let you, I'm going to just work with the entire screen then. Allow. Okay, so you probably see my screen at this time.
Yep.
Now you see my smoke emissions questions. Do you see that?
Yeah. Do you have 2 monitors? Because it looks like you're just sharing one of them. That's the only.
Yeah, I know. I got a display swap. Okay, I think that works.
There you go. That looks probably better.
Okay. So my apologies. Okay. So you see the next slide here?
Yep.
Where I talk about rate of spread, fuel consumption, fire intensity, and buoyancy. So when I did a quick survey of the answers, it was just fun to see the mixed results here. As I said, rate of spread, there was no clear answer. Fuel consumption, a majority, well, half the students were saying that it increased the ground level smoke. Fire intensity, again, another mixed package. And then when it comes to vertical instability, a majority of the students said it decreases the ground level smoke. So I just kind of did a little visual exercise here to show how this might affect things. And again, you know, This is just my interpretation of things. You folks probably have, a lot more experience than I on the ground, boots on the ground, such. But from a modeling perspective, this is what's going on. So I've just got a little fire here, 3 squares long, dumping out a certain amount of smoke and kind of a 50% gray. So if we increase the rate of spread, what do? All the other things considered equal, the fire continues to last 3 time steps. So here we are lasting 3 time steps. So what ends up happening is the area burnt increases, but the concentration of smoke above that area actually remains fairly constant. So in a sense, the rate of spread doesn't really affect the concentration of the smoke too much. Fuel consumption, on the other hand, we're dumping a lot more smoke into the atmosphere. So we're actually increasing the amount of smoke concentration because of fuel consumption. If we look at buoyancy, what we're doing is we're stretching this smoke that's being emitted to higher levels. So we're decreasing the amount of smoke. Well, when it comes to fire intensity, this gets tricky because if we look at Byram's equation, there's an equation, guys. Don't get scared. I equals HWI, where I is the intensity of the fire, W is the weight of fuel consumed, and R is the rate of spread. So I can increase either of these two ways. If we increase the fire intensity through fuel consumption, we're heating up this mass and the buoyancy is lifting it higher. So in a sense, the increased density, which we saw here, gets stretched. So kind of like a plus and a minus kind of comes up with kind of a relatively net zero effect. Now, if the fire intensity increased because of rate of spread, it would be the same amount of area burnt, but again, vertically stretched. So it would probably actually decrease the smoke, okay? With all that said, I just want to be clear, there were no easy answers to any of these questions, okay? It was just a way to get you guys thinking about smoke and looking at the responses that came in and the justifications one way or another. I got a good kind of, I enjoyed that little thought exercise. I appreciate that. Okay, so I'm going to end this show and we're going to proceed to the real show here. Did anyone have any questions on that exercise? I'm not reading the comment section, so I don't know. I'll have to ask you to voice up. Yes?
Carrie, the comment I put in the chat was without the all else remaining equal part of it in the question, it wasn't clear to me what would happen because there's multiple ways to achieve a higher rate of spread and they'll all have a different effect on the smoke, right?
Yeah. Well, again, I'm sorry, I could have perhaps been a little bit clearer about that. I thought I was, but I appreciate that. But again, the exercise was there were no marks involved. The intent was to try to get you thinking, and indeed, even questioning my question has got you thinking, which is again a very positive result. So, any other questions at this stage? Okay, well, I will then proceed with the actual class here. So I don't have my oh, there's the time here, 1:20. Okay, so again, this is a smoke modeling, and it's directed towards the fire behavior analysts. Okay, again, my background: I'm a former research scientist with Natural Resources Canada. I did a lot of fire behavior modeling, fire growth modeling, fire occurrence prediction, and towards the end of my career, I moved into smoke modeling. And indeed, when I retired, Environment Canada picked me up. A very quick outline of the talk. We're going to discuss introduction and then move on to physical principles. This will include atmospheric stability. I'll talk about the various measures of smoke, common measurements. ways of measuring smoke, then move on to the various monitoring networks that are currently available. The physical models is important to understand how the forecasting tools, whether it's blue sky or firework. And then finally, I'm going to discuss Blue Sky Playground Canada, which I regret to say is not functional. They're in the process of upgrading it, but I shall present it regardless. So, introduction. I'm kind of coming into this a little bit cold. I don't know many of you personally, so I don't know what sort of background you have. But I mean, what's the first question in my mind? Let's get this stupid thing out of the way here. Kind of think about it. Is you're the fire analyst. You're worrying about fires burning and houses being impacted, whatnot. And why are you worried about smoke? Well, that's because well, it's certainly tragic when dozens of houses or more are destroyed by fire. The smoke that gets generated by a fire can blanket entire provinces, and this ultimately affects the safety, health, and well-being of Canadians. Every year in Canada, we typically see about 6,000 forest fires, resulting in dozens of evacuations. Health alerts impacting the lives of millions of Canadians are issued each summer, indicating the negative health effects of smoke exposure. And of course, industry and tourism are also affected by this. For example, last year, the Canada Triathlon Ironman, which is held in Penticton, ended up getting canceled because of the smoke concentrations. Imagine how that impacted all the hotels and whatnot because of that. So here we are. What are the health impacts? Well, mainly what we're focusing on here are chemicals like pollutants like carbon dioxide, carbon monoxide, NOx, other various volatile organic components. But quite often what we talk about here are the particulate matters, or particulate material, or particulate matter, whether it's PM10 or PM2.5. And these health effects are known, but studies limited to the impact of wildfire smoke are limited. Essentially, what's happening is the smoke that people are breathing in. This is on a very fine scale, and as you can see here with the picture of the lung on the left-hand side, the smaller the item, the deeper it goes into the lungs, and indeed. Even smallest particulate matter, less than 1 micron, and well, 2.5 as well, will actually move through the lungs into the blood system. So it impacts the whole body. Another way to think of this is in terms of cigarette smoking. You know, there's a study here that compared the impact of PM 2.5 and compared it to smoking equivalent. And as it turns out, about 5 micrograms per meter square, or per micrograms per cubic meter, I should say, of PM 2.5 is equivalent of smoking a cigarette. So if the PM 2.5 is up to about 50, you're smoking 7 to 10 cigarettes at that level. Again, here's a link that's provided if anyone wants to follow up on any of these web pages I bring up. Evacuations. Many evacuations are caused because of smoke, impacting a lot of northern communities. For example, 2024 wildfires resulted in the evacuation of 50% of people in the Northwest Territories. Whether that was due to fire or due to smoke, I don't have specifics, but that was an example. And each evacuation disrupts lives and livelihoods of residents and their families and communities. Smoke events, as I say, can blanket vast areas and impact urban centers, affecting thousands of people at a time. You may recall what happened last spring when the fires in northern northern Quebec were actually billowing out and impacting the U.S. seaboard. From the news stories that suddenly perked up because of that. Well, here's the example. On June the 7th in 2023, the air quality index was above 480 on Wednesday evening in New York City. Technically, this was off the chart. This normally goes up to about 300. The pictures here clearly show how what the skyline looks like on a clear day, which maybe in New York City you don't see too often, compared to what you saw on that specific day. The map here on the side here is showing the extent of that smoke impact, as well as the timeline here showing how high the values got over the course of time. So there's a certain urgency to try to inform people about the importance of forecasting the smoke, because this is important to inform the public, as well as health protection agencies, hospitals and whatnot. Fire management agencies should be well aware of the impact of smoke, and other federal and provincial departments. And the question is always, what is the most effective way of passing this information on in a timely manner? Well, keeping that point in mind, I want to go back and review some of the principles of smoke. Central problem of predicting smoke is estimating the amount of fuel that's consumed by a fire, which in turn is injected into the atmosphere. Estimating the amount of fuel consumed amounts to calculating the total mass of biomass consumed, which becomes a product of the fuel consumption per unit area, for example, from the FBP system in kilograms per meter squared, or tons per hectare, or whatever unit you want to use, as well as the burnt area. As I say, this product, we can see from the FBP system that we do come up with methods of calculating the fuel consumption from fires. This is dependent primarily on the buildup index, for example. Although in some other cases here, it's dependent on the FFMC in C1 fuel type. As fuel's consumed, it turns into both smoke emissions as well as energy, and this happens over the course of time, and this leads to buoyancy as well as and smoke emissions. This can be divided into, we tend to divide the fuel consumption and smoke emissions into 3 stages. We think of this as the flaming stage, is illustrated on the bars here. The flaming stage, which typically happens in the first hour or so, the smoldering stage, and then the residual stage, which occurs after the fire front has passed. These in turn burn through the top layer, the litter, and then the fermentation, and then the deep humus layer. Depending upon the stage of the fire, certain amounts of, for example, a majority of the fuel consumed in the litter layer is consumed during the flaming stage. Same with the crown. While on the other hand, the deeper layers are consumed during the residual layer. Okay. Well, as it turns out, once we have this information, we can calculate chemical species emitted during the 3 stages of flaming, smoldering, and residual. So this provides us a means of calculating species emitted over time. If anyone has any questions, by the way, I'm afraid with this full screen mode, I can't see if anyone has any conversations going on the side. Do just pipe up. I'm a pretty dynamic speaker. I can go off on tangents if necessary. But I'd rather be kind of have a clear picture of what's going on than me rambling on and the folks being totally confused. Or maybe you guys are really brilliant and you know this stuff already.
Smooth sailing so far, Kerry.
I'm doing fine. Okay, good. Well, that's encouraging. So I want to move on to talk about one of the important factors in understanding smoke and smoke concentration is the stability, because the stability really drives at what vertical level the smoke affects. If you've got a buoyant, if you've got a stable, or if you've got an unstable, sorry, my apologies, an unstable situation, you've got a lot of vertical mixing going on. The smoke gets lifted aloft, and the concentrations near the ground are often quite low. On the other hand, the flip side of that is under stable conditions. The smoke will stay close to the ground, and this depends a lot on stability, which I'll discuss later. Another way to look at this, and this is a very fascinating figure, by the way. This is created by Roland Stahl many years ago. It shows how the atmosphere evolves over time. During the day, we often have what's called, on the left-hand side, let's see if I get my mouse here, what we call the convective mixing layer. So this is where you get your puffy cumulus clouds going. You got it's a nice warm day, you got puffy cumulus clouds. But as the sun sets, the surface starts to cool. The surface layers start to cool because of radiative cooling. And you end up with this stable nocturnal boundary layer close to the bottom. You still have that mixing layer, what they now call the residual layer, but this is above the stable boundary layer. And then when the next morning comes along, you get sunrise, and the convective mixing starts to grow. But in the meantime, you end up with often what you end up is what we call a capping inversion, which is basically kind of the transition from the overnight cooling to yesterday's convective mixing. And this is actually you can see this quite often in upper air soundings. I don't know if you've talked about upper air soundings yet in the talk, but this is a good example, because what you see here is this is the residual layer. This is yesterday's mixing layer. And this is the cool layer caused overnight. But now what's happening is you've got mixing occurring in the very early morning. This is Edmonton at 12 o'clock, 12Z, which is about 6 o'clock in the morning, give or take an hour or two. I can't recall what time zone. But this is a good example of what they call a capping inversion. So in this sort of a situation, all the mixing is happening close to the ground, and the smoke, if you'd have a fire, maybe a smoldering fire, all the smoke would be trapped in this low layer, and this capping inversion would keep it kind of squashed to the ground. Here's another illustration. I got lots of illustrations here going. Maybe I'm speaking to the choir or preaching to the choir. You guys probably know all this stuff. But depending upon a stable atmosphere will keep the smoke close to the ground. But as the mixing goes on, as the atmosphere gets more mixed, you will see this smoke being lifted aloft until finally, here in a highly unstable atmosphere, it might be lifted all the way to the tropopause. This might be a pyrocumulus, for example. Now, if you talk to any Canadian meteorologists, they don't like those other upper air soundings. They prefer the use of tephograms. What the heck's the difference? Well, this is actually a crafty little graph, because what the X and Y axes here are red and black is the temperature, the potential temperature, which means absolutely nothing to you guys, I know, but the nice thing is, by using these axes, area on this graph is directly proportional to energy. Where did my mouse go? And it allows meteorologists to very quickly assess stability and estimate the energy of cloud involved in cloud physics. How this affects smoke from forest fires is as I say, with a tephogram, where did my mouse go? Oh, there we are. Okay. So here's our smoke. And because area is directly proportional to energy, if we know what the energy of the forest fire is, we can calculate this energy on a tephogram, and we can calculate exactly how high the smoke plume will go. And indeed, this technique is used in many of these smoke forecasting models I will talk about later. So how are we doing so far? Everybody confused yet? Good, because I'll just keep on layering it on then. Oh, yes, a question?
No, we're not yet confused.
Good. I got plenty of time still. Okay, let's keep on going. So, yeah, air quality in terms of
Hey,
health
Gary,
concerns.
there is a
Yeah.
question. There is a
Oh,
question. Since you said you
yes.
wanted to be interrupted, we'll interrupt you. So
Absolutely.
Danny in New Brunswick asks, does the lower nocturnal layer sometimes not happen, and why? Is there a weather event we should be looking for to stop this from happening?
Well, I mean, it's hard to stop this from happening, but a lot of this has to do with I mean, if you've got a cloud cover over top, if you've got an overcast layer, there's less radiation being released into the upper atmosphere. So this is kind of this is a situation where I wonder where the mouse is. Okay, there we go. So you got to think that all the heat is going from the surface. If you've got a cloud layer here, that heat will go to the cloud and then get sent back to Earth, to the surface. So you will not develop the same nocturnal boundary layer that one would see on a clear night. On a clear night, the energy would just go up and up and up and up, and this boundary layer will really you'll get a really strong capping inversion the next day. Does that answer your question there, Danny? Okay, let's assume it does. So again, depending upon if there was a cloud cover over top, we would not see this sort of capping inversion. Any other questions at this stage? Nobody wants to have a question about a tephogram? No? Okay. So let's carry on at this stage and talk about measurements. So what we're looking at here is in smoke, we're looking at from health perspectives, is we're looking at a number of factors here, not just from smoke, but from other pollutants. For example, ozone. These are often urban pollution components: nitrous dioxide, sulfur dioxide. Well, PM 2.5 and PM 10 are typically what you see, and carbon monoxide is what you typically see from in forest fire smoke. As these numbers go up, you expect the air quality to go down. So for example, here's PM 2.5. Remember I was talking about cigarette smoking? Well, if you ever hit around 50 or so, you're starting to get into the unhealthy range. And that's both for PM 10 and PM 2.5. I apologize. This link is actually to Ireland's air quality index, but the principles still apply. In Canada, we have what's called the Air Quality Health Index. And it comes down to a simple equation, as shown below, which is just a combination of PM 2.5, ozone, and nitrous dioxide. So remember this question for the exam, and you'll get 100%. And if you don't remember it, you probably still will get 100% because it won't be included. Don't worry. Now the scale of the Canadian system is from 1 to 10 plus. So in really terrible situations, you might see an AQI of 20 or higher. But generally speaking, you'll see the air quality index between 1 and 10. And if you go to Environment Canada's webpage and you look for the forecast for Toronto, Usually there's a little button there that says, you know, for air quality, and you can pull this with the value up for Toronto on that given day. The US has a slightly different system. Rather than 1 to 10, they have a scale that goes from basically 1 to 500, where each component within the measured in the AQI, considered in the AQI, this includes ozone, particulate matter, carbon monoxide, sulfur dioxide, and nitrogen dioxide. These are measured on a scale of 0 to 100 each, and then added together to give you a value of up to 500. So this is going to be different from the Canadian system, AQHI, AQI. Another measuring system that's used is the atmospheric dispersion index. Now this is getting a little bit long in the tooth, 1986, but it's still used, and indeed it's presented on the Canadian Wildland Fire Information System. So the atmospheric dispersion index gives us a sense of how easily transported the smoke would be away from a fire. And this becomes a function of the ceiling, how high the cloud ceiling is in the case of 50% cloud cover. It also depends on the stability, the mixing layer height, and the transport wind. So the higher the ADI, the more likely smoke would be dispersed. And on this day in June 13th last year, that's when all that smoke was hitting the East Coast, and you can see that the ADI values are very low. Moving along, we go on to the topic of monitoring networks. But before we do, were there any other questions at this stage? Very good. I'll carry on. So there's a number of air quality networks around the country. As I indicated earlier, you can pick out your favorite. You can go to Environment and Climate Change Canada's webpage, and by selecting your city, for example, I live in Summerland, BC, so I was able to go to Summerland. I hit a button that sends me to the air quality, and so it gives me a measure of the air quality in the South Okanagan here, and you can see, I'm sorry, it's not quite that, it's a little bit small, but you can see that the air quality rating on this day, February 28th, in the middle is 2, so it's very low risk. A number of provincial and regional a number of provinces as well as regional areas also have their own air quality networks. And if you follow various links, you can often get to a point where you can get measurements showing the air quality. Again, here it is Penticton, very close to where I live. I was able to go to the BC Air Quality webpage, and clicking through, I was able to get measurements of PM 2.5. And here you can see the measurements over the course of time. I provided various links to provincial locations. So if you download this PowerPoint, you could go to your favorite location and pull up these sorts of maps. An alternative to all of this are various commercial air quality monitors. Indeed, I even bought one of these. So if you look for the air quality in Summerland, you'll see my device, which is out on my downstairs patio. By reaching out to the general public who are putting these at their homes, as well as official devices by provincial and regional networks, you can pull up maps showing the air quality in real time. These are very valuable. I often go to these. So 2 companies here. I'm not promoting one or the other or others, or but one is IQ Air, and the other is Purple Air. And you can pull these up, and you can get the air quality anywhere in the world. So these are very fascinating web pages to go to. Now, before we go on to predictive models, change the topics. Were there any questions about the networks before I move on? I gather not. So at this stage, before we get into the actual forecasting models, I want to talk about the physical processes involved in modeling smoke. One of the traditional ways of modeling smoke is what they call a Gaussian plume model. That's where you basically take a plume and it spreads over time. So as the plume evolves downwind, it widens in both vertical and horizontal directions. And the density of the smoke follows what we call a Gaussian or bell curve distribution, as shown with the figure in the bottom right, the green line. So as we get towards the center of the plume, the smoke density is the highest, but as you move towards the fringes of the plume, the density drops off. This is a common technique to model smoke plumes. So as long as you have a sense of how far the smoke plume goes, how high it goes, you can come up with a simple scheme to come up with a measurement. As you move into more sophisticated modeling, and don't panic, this is not going to be on the final exam. We talk about what we call Eulerian and Lagrangian modeling techniques. Why do I get into this? Well, it's important to understand that Eulerian kind of has a fixed grid. So imagine a big checkerboard, and you can calculate what the physical values of, for example, temperature, wind speed, whatnot, humidity, and as well as smoke density on a fixed grid. And using just basic modeling techniques, you can spread that smoke into adjacent grids. This is kind of a technique that this might be something like an 8-point fire growth model would use an Eulerian type technique. On the other hand, you've got what's called Lagrangian, which is instead of following a fixed grid, you follow points of motion. So imagine that as a particle evolves in time, you follow its trajectory and you calculate how it evolves as it goes along. An example of a Lagrangian model would be Prometheus, because you're calculating elliptical growth at various points and conducting what do you call the elliptical growths, the Huygens wavelets. But anyway, that's an aside. A third approach, well, a fourth approach actually. A fourth approach is what they call puff models. And indeed, this is what Blue Sky uses. So a puff model is kind of a combination of both Gaussian and Lagrangian techniques. Where what we're doing, if I can find my mouse again, is we take a puff of smoke. So the fire will emit a puff of smoke every minute, every 15 minutes, whatever. And we will model how it evolves over the course of each time step. We will follow how this puff moves over time, and we'll calculate how much it expands over time. So all the characteristics are being calculated per puff. And these puffs are kind of moved along over the course of time. Okay, how many people are still aren't confused yet? Okay, let's hope not too many. At this stage, we're going to talk about first the firework model. So the firework model is the Environment Canada produces the firework model. It is run it's run twice a day, and it's run in Canada and North America, so you can actually see the evolution over time in Canada. So these are based on typically reported fires, which are typically collected as hotspots, satellite detected hotspots. And then smoke is emitted from these based on the Canadian Forest Fire Emissions Prediction System, CFEPS. So the amount of smoke and how high the smoke is ejected into the atmosphere is calculated. Then a handshake occurs, and that information is passed on to Environment Canada's big super duper weather model, the GEM model, and it is dispersed over time. So these maps are produced and are available every day, twice a day, for all of North America. And Firework uses an Eulerian modeling approach. The Blue Sky Canada, often referred to as Fire Smoke Canada based on the web page, is also very popular. This comes out of UBC, and the folks, Roland Stoll and the gang there, do these calculations. This is a model that was originally developed in a cooperation between a number of provincial agencies, BC and Alberta and others. And it was based on the Blue Sky framework originally developed by the U.S. Forest Service. So the Blue Sky framework was ported to Canada, and the folks at UBC are running the model. So similar to Firework, it takes the hotspot, the satellite detected hotspot information, and calculates the smoke emitted from these. In the Blue Sky Canada approach, it calculates it using the PUF model. And they run this model 4 times a day using data from CWFIS. I should mention that Firework Canada also uses the CWFIS data. And also, Blue Sky Canada runs what they call the playground model, which I will discuss next. What playground is it's an interactive tool. So that if you're if you're thinking of doing a prescribed burn and you're worried whether the smoke will impact neighboring locations, you might want to run Playground. Through Playground, you can enter your own information. You can enter the size of your prescribed burn and the fire weather conditions associated with it. And then by pressing a button, you link it to the weather models, which will end up giving you a prediction of what the smoke plume will look like. Another system that's worth mentioning is VSmoke. Again, some of these models are getting a little bit long in the tooth. This is an older model. I guess it's about going on 30 years old now. But VSmoke and VSmoke GIS are being used in the US playground system. This is a simple Gaussian model. So if you can remember that Gaussian curve, the bell curve, estimating the smoke, and they just spread it directly downwind. They consider how stable the atmosphere is. They consider you enter the wind direction and the wind speed, and it just calculates a simple downward spread, sort of like Prometheus does. But it's not 3-dimensional. It's just a 2-dimensional model, more or less. Here's an example on the side. If you can see my mouse, I can't see it. But anyway, on the right-hand side, yeah, you could enter the lat long and the size of the forest fire, and the type of fire you're trying to model here, and that information gets passed to produce the smoke plume. High split. Okay, I'm just trying to be complete here, but again, high split is the model that's being run by the U.S. in the U.S. National Oceanographic and Aeronautic Administration, NOAA. Their Air Resource Laboratory runs it. It was developed by the ARL as well as the Australians. It's a Lagrangian model. So if you can imagine what it does is you can run this program, and there's the mouse. You can run the program, and by entering a location, you could ask it to predict the particle paths downwind. This is used for forest fires as well as volcanic activity and industrial incidents. Okay, that pretty much kind of captures the bulk of all the various models that can be used. Certainly the Blue Sky Canada and Environment Canada's firework are probably the two you'll refer to the most, I guess. You'll be probably looking at those on a daily basis to get a sense of what the smoke is doing on a given day, or explain maybe to the public where the smoke is coming from. But at this stage, I want to move into this interactive tool called Playground. But before I do, I just want to open the floor again, open to any other questions or whatnot. Any comments on the comment bar there, Dan?
Oh, Sebastien has shared a couple nice photos of some big smoke plumes, and
Yeah.
Danny didn't buy your explanation about the lower nocturnal layer. You said
Well, that's
you're
too
way
bad.
off.
Too bad for him. No, if you
No, he
guys
just
have any
said-
further questions, you can certainly talk to me on the side.
No, I'm just joking. He reported that clouds, are known to inhibit fire growth, and so just thinking about your overnight roll install profile there in the context of nighttime fire runs.
Well, I'll let you in on a little secret here. What we're trying to do in firework, I mean, they keep on rehiring me. I'm not too sure why, but they keep on rehiring me, and we keep on adding additional information onto it. One thing we're trying to do is we're trying to evaluate, we're trying to incorporate a feedback process where the model will calculate the amount of smoke that's being injected into the atmosphere. But at the same time, that smoke is going to affect the surface meteorology. Indeed, I forget what year it was, a couple, 3 years ago, there was an incident where Environment Canada was predicting for Edmonton a temperature of about 25 degrees, and it ended up being off by over 10 degrees. That was down into the low teens. Why did that happen? Well, it was because there was a big freaking smoke plume over top of town, and it was blocking the sun. And the temperature was off by like 13 degrees, the forecast. That caused a lot of friction within Environment Canada, and there was a real concerted effort to try to find a way to link our forecasts, our smoke forecasts, to the public weather forecast. So there are things like this in the works. I can't speak for Roland Stowe if his group is doing any similar sorts of studies, but such interactions are being considered.
So, Carrie,
Yes?
like along the same vein, I was wondering when to ask that. Like until it does make it into the model, like as FBAN operationally, if we're looking at this and we know we have a forecast of a certain temperature, a certain RH for the day, which would like trigger extreme fire behavior, but you kind of like see that you're probably going to be under cloud cover or like a smoke cover, shading from smoke.
Yeah.
Like how should we approach this? Should we kind of like give a forecast of like without the smoke and then kind of explain that, but if I increase my RH and lower my temp because I think that's what the smoke's gonna do, this isn't actually what you're gonna see? Like, do you think that's a good approach to kind of?
Yeah, I'm not qualified to tell you how much to reduce the rate of spread or anything like that, whether you knock it down 10 or 50% or anything like that. But it is well known that the smoke plume, especially in a situation where the smoke is it's the anvil that's going over top of the burning area, it will reduce the rate of spread if it's sufficiently thick enough. And these are factors to consider. Flip side of that, of course, is the pyrocumulus technique, considerations too, which will actually amplify fire behavior. But that's where your expertise kicks in. I'm just a modeler. I might know my atmospheric thermodynamics really well, but it will be up to you to make that judgment call. But efforts are underway to try to link fire growth modeling into, the smoke plumes from fire growth into the fire growth models. But I can't promise how soon that will happen. Any other questions while we're on this topic?
Kerry, I'd be happy to know. You showed us a whole bunch of models. I think many of us have seen, or at least been referred to, Firework and Blue Sky.
Oh, these models, okay.
Smoke models. Like, which is better? I don't know. What are the quirks?
Well, of course. And I work for Environment Canada, and this is the best.
Is it because it's Eulerian?
Actually, the thing, it's not, honestly, it's not so much the modeling technique per se it's the horsepower behind this model, behind Firework, that probably gives it a better result than Blue Sky. I don't want to badmouth the Blue Sky folks, but Environment Canada and whatnot, these guys have supercomputers that really just knock the wind out of something that can come out of a university like UBC. UBC, on the other hand, is a very interactive. You can work closely with them, and I think they're very accommodating to user needs. Environment Canada, on the other hand, is a kind of a big department that doesn't quite react as quickly as other small universities may to user needs. But if I may kind of state quite honestly, it's the difference between a Volkswagen and a Trans Am. Okay, that's what we're talking about here.
You got a couple more questions here. I guess
Sure.
Sebastien was first.
Sure.
Yeah, Kerry, I was wondering, can you guys have some kind of model, something that could figure if you have like a big amount of smoke there and works almost like an inversion sometimes, like it just lowers the all the intensity and all of that of the fire, just like inversion. Can you guys predict and the amount of time which the sky is going to clear itself and just be in a more unstable air part of can you predict that?
Well, it would be nice. And I suppose, if somebody kind of focused their attention on specific questions like that, you might get an answer. What I would like to maybe see, and who knows if somebody might develop it soon, would be some sort of a fire growth model like Prometheus or whatnot that would have smoke as a consideration into it. Hopefully, this would kind of impact the weather conditions surrounding the fire, and that would in turn be cycled back into the fire growth model. I know that there are products, for example, one that comes to mind, of course, is Fire Tech, which was developed at Los Alamos. But Fire Tech requires a supercomputer, and it takes 12 hours to create a 4-minute simulation. This is not quite the scale that the operational people like you need. I know that there are other models out there that have coupled fire growth and atmospheric conditions in them. I think it's S-Fire out of NCAR and others that may be promising, and so there is the potential to do what you're asking. But at this time, I honestly, we're not quite at that stage yet, but it's a possibility.
Norma has a question too.
Sure, let's keep them going.
Actually, it's not a question, but a commentaire. I use Blue Sky and Fireworks. I prefer Fireworks since many years. It's not scientific, but for around 500 kilometers from the source, Fireworks is very accurate for the location for the smoke plume. And the most common error people are doing, they don't use the good map to make some prediction for the surface. You
Yeah.
have some maps for the 3,000 feet. You have some map for a very high, but you have some maps to the ground. So you have to use the good one. This is a
Yeah.
trap. Also, I think Blue Sky it has the same amount of smoke production per unit of surface.
Yes.
I think, and firework use a number more appropriate from where the fire is, I think, from my remembrance. Isn't it? Is it right?
Yeah, well, actually, believe it or not, they use we use the same fire locations.
Okay.
The out of Edmonton, Natural NRCan through the CWFIS creates all the hotspots that are used by both models. This is not I should like also kind of be very clear that this isn't a competition between two models. It just happened that that Blue Sky was originally developed, and Firework kind of followed closely afterward. But there's a lot of common elements in it. What's different, of course, is the horsepower that's used to drive the two models. And as I say, Environment Canada has all these supercomputers driving this. But on the other hand, Blue Sky Canada has a lot more interaction, including the Blue Sky Playground, which is a very useful tool. I just apologize that you pick the year when it's not running, but they hope to get it up and running again soon.
Okay, that's great. And I've been asked often to make some visibility prediction for the people who drive on the road or for the plane. And I came out with a number at 500 microgram per square meter.
Yeah.
Then the visibility is reduced under 800 meters.
Yeah. Well, I mean, if we go back to those pictures of New York City, that was about 500. 500 micrograms per cubic meter. Okay. So, I mean, you'd barely see 10 feet ahead of you at that level.
Yeah.
Okay. But certainly anything above, probably above 100, 200, you're going to start to see reduced visibility. Certainly.
Yeah. On the fireworks side, there's Wimei Lee from Environment Canada. He wrote that 5 to 200 microgram, it reduced 5 to 10 kilometers, and then between 200 and 500. So he put some numbers. So that's why I used them.
Okay. No, this is good feedback. I appreciate that. When I talk to our team tomorrow, I'll suggest, if there's some way of kind of coming up with a visibility, But again, this is where you're dealing with a big institution. I mean, I might ask this, and it might take 2 years for them to get around to doing it. So,
it's pretty accurate. But there's only one thing I don't think if they use it, if it's more humid, it acts as a nucleus, so particle becomes bigger, so the visibility reduction is higher when it's more humid.
Oh, okay. Okay.
I don't know if they used it. I got it from Chinese. They are very good at it in Chinese.
So you're saying the humidity will reduce the visibility with smoke? Oh, yes. Yeah. Well, of course, you're talking now. No, I'm kind of cluing in. You're talking about super fog.
Yeah.
Which is something that often occurs down in the southern U.S. states. The humidity and the smoke they mix together, and they just the visibility is drops down to practically nil. I don't know much specifically about it. I couldn't answer your questions, but if you look up super fog, do a Google search on it, you could probably find a lot of information on that.
Thank you.
Yeah, forgot about that. That's a good discussion point. Anything else while we're on the topic? Okay, I'll just keep on
Sure.
moving on then, if that's all right. Oh, sorry.
No, just said thanks. Yeah, that's it for now.
Oh, okay, okay. So what I wanted to do here was I wanted to quickly go through an example of what Blue Sky Canada Playground, how one runs it. But as I say, unfortunately, the system is not running at present, so you won't be able to run it. On the other hand, the US model, Blue Sky Playground, just take out the word Canada, is available, and I provided links as well as a sample exercise that I'll let you guys do at your own convenience. I'm not gonna ask it to be a marked exam or anything like that. I'll just trust you guys to follow up, and you can contact me later if you have any questions. Okay, but I will walk through what Blue Sky Canada used to do, and hopefully will do when it gets functional again. So how Blue Sky Canada works, as you can see here from the bullets, you pass along the fire information, fuels, consumption rates, emissions, and then the meteorology. And from there, it calculates the dispersion. So the model is based primarily on a lot of Canadian systems. That's why it's Blue Sky Canada. So it takes advantage of the CFF-DRS. So you could add your favorite FWI values, use your favorite BUI, or pick your favorite FBP fuel type and use that. The system uses the FEPS model, the Fire Emission Prediction System, to estimate how much emissions are released from the fire. Then it uses high split to disperse this smoke downwind. And finally, it's being driven by the WRF model, the Weather Research Forecasting Model, for its meteorology. This is the horsepower I was talking about before. This is not quite as robust as the Environment Canada's model, but I won't criticize it too much. So again, you're basically on the left-hand side, you're entering all those orange values, and then you provide and then Blue Sky Canada Playground provides a link to the meteorology which you choose, and then it comes up with the dispersion. So again, as a user, you type in the fire location, you choose the FWI and FBP information that goes into the model. The model then calculates the types of emissions that comes out, combines that with the meteorology to calculate the dispersion. Fire information. Well, it's pretty basic. You're kind of here's a picture of the dialog box. And as shown in red, you're entering the latitude, longitude, as well as the size of the fire. Also on the left-hand side, you're entering the type of fire, whether it's a broadcast or piles or wood fire, wildfire. Oh, there it is. Okay, as I was trying to say. So on the left-hand side, you're choosing whether you want to run a prescribed fire, whether you're burning off wood piles. Oh, I got the mouse. Okay. Or whether it is a wildfire. And each of these types of fire have different characteristics. That's why we have to specify which one's which. So I guess latitude, longitude are pretty obvious. Size of the fire is pretty obvious. So prescribed burns, you guys know all about this stuff. Controlled burns conducted to accomplish, fire management plans. These are the easiest to control, and the decisions associated with an attempt to minimize the emissions and impact on the local communities. Pile burns typically used by forest companies. Come November, all that forest debris gets piled up and they're burnt. Maybe provinces can only provide guidelines to this, but it's very useful to have knowledge about this. Wildfires, of course, are non-intended. They're unintended fires that occur in the landscape. Not too much you can do about them except do a really good job of fighting them as FBANs. Certainly the amount of smoke from wildfire could cover vast areas. Oops, wrong way. Fuel loading. Now, fuel loading, you're passing this information on. What's driving it is the FBP system. The FBP provides guidelines, and certainly you went through the exercise this morning with Dan talking about fuel loads. FBP has fixed fuel loads, but in theory, you'd be able to adjust these. All of this stuff gets fed into the FBP and the FWI system, so you would enter above here. Let's see, where's my mouse? So here you'd enter the fire weather conditions, whether it's your favorite fine fuel moisture code you want to burn at, maybe 90 or something, as well as other conditions like the depth moisture code, drought code. It would then calculate the ISI, BOI, and fire weather. Based on this information, on the left-hand side, you could choose the type of fuel type you want. Here's you're entering the fire weather conditions. This is the outputs that come out. Okay, I'm getting ahead of myself here. So this is the information you're adding, as well as timing of the inputs. If you're burning a pile, you might want to describe. You have an ability to decide how the characteristics of the pile, like the shape of the pile here. Here we've got a kind of a hemisphere of a big round hemisphere of wood, but you can choose whether you want a pyramid or other type. Also, the type of wood that's being burnt and the amount of soil, how much dirt you expect in the pile. All this information you can add in. And then from this point on, it starts to do its own calculations. So the consumption rate is calculated based on the information you fed into it. It will calculate the amount of fuel consumed per hour. And depending upon what type of burn it is, you've got certain characteristics that come out of this. And that feeds how the smoke is being generated over time. As you can see here on the right-hand side. The emissions are pre-calculated. Again, these are fixed rates. They depend a lot on the bulk densities and various depths of forest floor. So all of this information is incorporated into the model. As mentioned before in the modeling section, I talked about the 3 stages of burning. So all these factors are incorporated into playground. So 90%, for example, 95% of the litter is burnt in flaming combustion, which happens in the first hour. And from this, you've again got the amount of per kilogram of wood biomass that's consumed. We get certain amount of grams of emissions, whether it's carbon monoxide, carbon dioxide, or PM 2.5 or PM 10. All these are being calculated within Blue Sky. You don't have to memorize these things. Finally, what you're going to do is you're going to link it to the weather, the best representative weather. Presumably, if you're burning tomorrow, you want to pick tomorrow's weather, and you choose it from the choices that are provided in Blue Sky. Afterwards, you hit the create dispersion button here, and you're off to the races. At this stage, the model is using a high split model to spread the smoke downwind. Again, high split is a hybrid approach, a hybrid of both the Lagrangian and Eulerian calculations. It also has plume rise developed into the model as well. The final product ends up being an animation that you can see in the Blue Sky playground. And you can see here how the smoke plume, shown in pink, grows over time. And you can slide the time. I think there's a button there. You can move the time back and forth to see how it affects things. You can look at daily concentrations, hourly concentrations, maximum concentrations.
Hey, Kerry, can I give you a 10-minute warning here? We're it's 2:20 and for the Eastern folks, it's awfully late and maybe that's me.
I've got
my
about
fault for
3
going
slides
late.
left. I'm almost done.
Okay.
Okay. Finally, what you can do at this stage is you can download it to a NetCDF or KMZ type file, which you can in turn bring into the Google Earth if you prefer to look at it that way. So finally, I just want to say, unfortunately at this stage, Blue Sky Canada Playground is unavailable. I was hoping to use it as an exercise for the class, but the folks at UBC apologized. It was just poor timing. They hope to have it running sometime this summer. In the meantime, the link is here that if you want to look at the the U.S. Forest Service Blue Sky Playground, if you can convert fuel types and use their 110-hour and 1-hour fuel moistures, you can play around and create much the same sort of situations. And the links are provided here. So that's it. Good timing, Dan. So that's the gist of it. I open the floor to any questions or comments. If I may, I'll close the presentation and slideshow, and I can read any comments that you folks have. Stop sharing. Any comments? I hope that that was a sufficient information at your level. I know that you may or may not be working very much with smoke. I tried to kind of like capture everything as much as I can. I hope that suited your needs. Okay, I put everybody to sleep here, maybe.
One of the questions I have, Kerry, I mean, all the like the business of venting, of course, if you're doing PBs, you know, venting, is the smoke gonna, you know, go nicely you know, up into an unstable atmosphere and be carried far away? I kind of feel like with you know, the recent fire seasons, I mean, these big smoke events were not caused by prescribed fire, but of course by wildfires. Like, you're keeping your neighbors happy, but does it all comes down somewhere, right? Like the smoke is just kind of being dispersed over a wide area. Like there's no real.
Yeah, I know. You know, what can one do about wildfire smoke? Probably nothing much, except inform the public so that they're well aware of what's coming down, where it's coming from, and how best to handle it, and not be surprised by it. So if the smoke is coming over your area, well, you better be prepared to be, you know, potentially evacuating communities. On the other hand, if you're talking about a decision to burn or not burn a prescribed burn, well, yeah, that's the decision you have to make, and communities will have to be aware of what you're doing. You don't want to get 911 calls from everybody wondering where the smoke is coming from. Sorry. Yeah, those are all big questions and things that you as FBANs should be aware of before you light that match. So, you know, that's why I'm discussing this.
Somewhere in between wildfires and prescribed fires would be ignition operations.
Well, certainly, yeah. I mean, you know, the whole fire business is always a balancing act of, you know, much of this is good for the forest, but at the same time, it's dangerous for the public, and you have to make those decisions. Certainly, fuel reduction is an important topic. You want to try to do those burns and try to, you know, minimize the amount of fuel in the landscape. But if you're going to annoy everybody in Camrose, you know, because of your burn, you know, you're kind of you're doing the best you can. But those decisions on what to do are based on knowledge and education, and that's really kind of what we're presenting here. Any other questions? Okay. Oh, we got a couple hands up. Are those old hands or what are those? Normand?
I think those are old hands.
Okay. Okay, good. Well, it's the end of the
Nope,
day. People.
there you go.
Lori's got a question.
I'll just
Please.
make a comment. This came up when I was doing some FBAN work here in Newfoundland in 2022, and we had highway closures because of smoke a lot during the week, which cut off an area of the island, and it got a lot of political attention. Anyway, in talks with Environment Canada folks on trying to see some of the smoke dispersion modeling things, they gave me or informed me of a web page which is similar to what you had said. And I just went to my favorites and found it, but it's a little different. I don't know if you can click and find it through what you shared with us, but it's a atmospheric transport and dispersion modeling, but it says it's an experimental system. And you actually bring up the map and it shows like the
From Environment
winds.
Canada?
Yeah.
Okay, I think I know those guys. You don't get actual measured values. You get kind of percentages. Is that correct? Like ratios of the density.
Yeah,
Anyway,
it showed a picture of the density
Please.
as it's dispersed, but anyway, I can share the link with you.
Yeah, I would appreciate seeing that.
Sure.
Well, it could be tomorrow or whatever. Share that with me when you get a chance. Yeah, I know that there's another group out of Montreal, CMC. They're kind of involved more in incidents. If there's a volcano that erupts, these are the guys that are like immediately responding and calculating plumes from disasters like that, or heaven forbid, a nuclear reactor exploding or something like that. These are the emergency response guys, and they have models to predict dispersion like that. Often they don't have units associated with that measurement though. And all they do is they tend to measure in terms of percentages. So the densest areas versus the least dense areas. But I'm basing that on conversations I had a few years ago. So that this may have evolved. But certainly it sounds like they probably put you in touch with those guys.
Yeah, I guess so.
And like even if you run the US playground, you can run the V smoke model and probably do a pretty good job of predicting where that smoke's going to go, especially if you're worried about highways being blocked. So
yeah, it's sad. And then they evacuated a community or the older population because of smoke, but I guess that happens quite often.
Yeah.
And
Yeah.
Where do you get to the parts per million or the measurement that you should be evacuating certain populations?
Well, that comes down to the various health departments each province has.
That's right.
I can't speak about Newfoundland, but I know that Health Canada's got guidelines, and for example, Alberta and BC have clear guidelines on when to kind of start acting. But what the state is in Newfoundland, I can't say. But I wouldn't be surprised if there's a department dealing with that.
Yeah, I'd say there is, and it probably brought more attention to that department to find the indicators when that happened.
Yeah. But these are all things to consider.
Thanks.
Okay.
All right, folks, it's been late, but many thanks to Carrie for the presentation coming. And Carrie, do you want to come to or arrange to come to an office hours session tomorrow, or do you prefer just people contact you independently? Or
well, I mean, people can contact me on the site. Certainly, I'm more than welcome to discuss matters with them. I've got my usual conference call tomorrow with Environment Canada folks at 8, but I could log in to the with the group at 9 o'clock, let's say, and be around for the morning for any questions or concerns people have. How does that sound?
That sounds great. Yeah, okay. we never really know. I'm going to be talking tomorrow as well, or I'll be there anyway, talking about some of the exercises for those interested.
Yeah. I mean, I've downloaded on the canvas the US playground exercise, and it didn't take me too long. It took me 20 minutes to kind of go through. If you have time to go through it, it's kind of fun it's a fun little toy to play around with and make smoke plumes. Okay, I'll let you go.
And with
Thanks
that,
again, folks.
I'm going to stop the recording. I think everyone's pretty